In chapter 2 of the book, we're studying this bandit problem as a case study. And we have this 10-arm test bed system where we are going to be given access to some random bandit where the rewards for each of the 10 arms are distributed randomly, but they have specific values that stay constant once the bandit has been defined. And the goal of this task is to both, learn as much as we can about these rewards. If we started out knowing these values, we would already know, which arm produces the most reward. But as we interact with this problem, we're trying to simultaneously estimate these values, learn which arm will produce the most reward for us. But, we're also trying to collect the most reward simultaneously. So that's where the exploration exploitation trade-off comes through. And most of this chapter is going to deal with techniques to actually balance that trade-off. But whatever technique we use, we have to have some way of estimating what these rewards are. And I know we had already been through this last time, but I'll just, to make things a little more obvious, I'm just gonna, write this down. Sorry, someone asked if I haven't, will you be able to understand if you join today? I'm gonna try to give as much background material as possible. There's also videos you can review. There should be a YouTube playlist in the link of the meeting description. But I'll see if there's any questions along the way. I'll look at the chat and feel free to interrupt and ask any follow-up questions. We'll go through as much of this part of the chapter as we can, as well as the exercises. So we all know that if we're collecting samples from some process, and our question is, what is the average reward for a particular arm of this bandit? So if we say we have data from an arm, I know everyone's going to say, well, it's really easy or obvious to compute the average, right? Like we just have this list of rewards, and then maybe up to in this case, I'm going to write it like, is this n-1 for reason it'll make some of the mathematical statements a little easier later. But this is a pretty straightforward thing to do. All we do is add up the rewards, right? And then we just divide by n-1. Oh, sorry, was there a question from someone? Oh, I'm just going to mute anyone that's, so there's less background noise. But yeah, if you do have a question, feel free to unmute yourself and ask. Okay, and then this would be right that this estimate, we have q sub n, right? So we can do this obviously every step, but in this algorithm, we're interested in doing keeping track of the average in an online fashion. Meaning, we have a stream of data, we already have some amount of data, and we'll be collecting new data. So, there's sort of an obvious way to do this, which is, if we look at this numerator, we can write down this quantity like Sn is equal to R1 plus R2 plus, plus Rn-1. And then in order to compute this thing we're interested in, all we do is we take the numerator, and then we divide by n-1. And then when we're interested in the next average, let's say we're assuming we already have this numerator value. Well, then, we're going to have some new reward value, but all we have to do is just take Sn, add the new reward value, and then divide by n. Right? So that's pretty easy. This way we can use the existing value for Sn, and we don't have to recompute this sum every time. Now, if we manipulate this expression a bit, like we can see that, if we have this expression, this implies that, Qn times n-1 is equal to Sn, right? And this expression, if we just multiply both sides by n, right, we have this is equal to S sub n plus Rn. Now we can substitute that expression for the previous sum of rewards. And then we get, this is Qn times n minus 1 plus Rn, right? Now, if we, starting with this expression, if we divide both sides by n, the only reason I'm doing this is to get an expression for the new average in terms of the old average. Now, here, right, we have this term is Qn times n. If we divide by n, we just get Qn. And then if we look at the next set of terms, right, if we distribute this out, this minus 1, we're going to get 1 over n, and then times, right, Rn minus Qn. Right? So, I mean, we don't actually have to do it this way. We can just as easily do this by keeping track of this sum in the numerator. And, we just add the next Rn to it. That's easy. But the purpose of writing it this way is because this creates an expression where we have some term which is the difference between the new reward and this is what we believe to have been the average. So you can think of this as like an error term. And then this is some constant, which we can think of as like a step size term or a learning rate term. Now, in the case of taking a sample average like this value is always 1 over n, which means that as we collect more and more samples, this the amount we weight the information from new terms is shrinking. It's shrinking as what with the ratio of the number of samples. But it turns out, we can compute different types of averages. And the next thing we're going to look at in the chapter is an average where we, instead of taking this constant to be 1 over n, we're going to just pick a constant value. Sorry, I shouldn't say constant. This in the case of the sample average, this is not a constant. This is a value that changes with every sample. But we can think of computing this average and replacing this 1 over n with some constant like alpha, which stays the same. And that will end up creating a different type of average, which will have advantages for the bandit problem that we'll see for the non-stationary problem. But we can also use it for the stationary problem. And we'll compare the performance of the technique in both of them. So yeah, this sort of derivation, I've sort of written it a little differently here in the notes. Right here is in the textbook, there's this derivation here, which they do in this way. This sum of R is like the numerator expression I've written down. But the whole purpose of this and these derivations is to update the average efficiently in an online fashion. Yes, yeah. So there are properties of this algorithm where, in order for this to converge, and it's actually covered in the book here. Actually, is it covered here or somewhere later? Let me check. Yeah, it's covered here. Okay. So the conditions for this to converge is that if we're computing an average and we have some step size parameter that we're using on every step, like in the case of the sample average, right, it's 1 over n. So, whether it changes per step or it's a constant, these two things have to be true in order for it to converge to the actual expected value over a long period of time. And that is that, if we sum up all of the constants, that sum diverges. Okay, so that is actually true of the 1 over n. And also, if we sum the square of all the constants, that doesn't diverge. So both of these have to be true, and both of these are true for the sample average method. When we do the constant step size method, then yeah, this is not true. So technically, yeah, this will not converge to the average. But we are introducing the constant step size method in the case of a non-stationary problem. So in the case of a non-stationary problem, there is no average to converge to because it is changing through time. And the point of the constant step size method is to track that changing average over time. But here, I'm getting a little ahead of ourselves. Let's go a little bit further back to the simple bandit algorithm that we had introduced. So this is using the sample average method. This expression here is the update rule, right, for the online update of the sample average, right, which is why we have the 1 over n here. And this method that we introduced is the epsilon greedy method for tracking or for balancing exploration and exploitation. So we normally pick the argmax of Q, which is what we currently believe to be the best, the arm with the best average. And then with some small probability epsilon, we select a random action in order to make sure that we're guaranteed to continue to improve the estimates for the other arms, right? And this, if we do this for an infinite amount of time, and also if epsilon converges to 0 over time, then this will be guaranteed to, in the limit, be able to select the reward with the best average in the long run. Right, and this is for the case where we have a bandit defined, all the arms have a specific mean value, and that stays constant through the whole process. So now we're going to move on to talking about the non-stationary problem. So in the non-stationary problem, we're going to consider the possibility that the bandit might be changing over time, or like whatever we're told about it, that the information in the past about what we've received, it might not necessarily hold completely into the future. I mean, it could be changing slowly, but we need a way to sort of eventually forget about past information. And the sample average method does not do that because, it weights all of the rewards, the entire history of rewards equally through time, right? They're all weighted 1 over n. And what we're going to show here is that if we modify the update formula so that the step size parameter is a constant, some constant alpha, I guess here, it's restricted to be between 0 and 1, then we can derive an expression where if we write this out, and here, we're taking this recursive expression and getting it into a form where we can then substitute the original recursive expression back into it. This is a derivation pattern that occurs throughout the book. Then we can write down what this update rule is actually doing. And what it's doing is it's still taking the sum of rewards, but the weight on each reward is exponentially decaying into the past. So the weight of the rewards received a long time ago and the long-term limit will be 0 in the limit, but they're being weighted less and less relative to the new information. There is also a dependence, as you can see here, on the first term. This also, as n grows over time, this bias towards the value of the first reward received, this bias also will go to 0 in the limit as n goes to infinity. But it is present in the data initially. So that's why this constant step size method of updating the average is called an exponential recently weighted average, because the terms, the weights exponentially decay into the past, and they are larger for the more recent terms. So are there any questions about this derivation, or like why we would do something like this for a non-stationary problem?
Can you please repeat the last statement?
The last statement. I don't. You mean about the exponential?
Yeah. Yes, yes, yeah.
Okay. Well, the exponential part is just that the term, the weight, the the weights on the rewards in the average exponentially decay into the past. So they are more highly weighted towards recent rewards than past rewards.
Got it. Thanks.
What do you have on the left there that has exercise 2.4 and some answers for it that I don't see in my PDF?
Oh, well, the PDF is the book. So the book does not have the answers to the exercise. These are my notes, which I use, to present. And yeah, my notes do have solutions to the exercises.
It also, for example, has different formatting around. If you scroll down where it says exercise 2.4, you can see on the right, it just says exercise 2.4, and it's in a call out on the left.
Sure. Well, these are my notes. They are not the same as the book.
Okay.
Yeah, but I will. Yeah, I mean, we also can go over exercise solutions here. Some of these exercises are only really useful to go over if you've done them yourself because they're kind of detailed with math. But this derivation, so this derivation in the book is showing if alpha is constant, then we have this sort of exponential recency weighted average. Exercise 2.4 is saying, imagine they are not constant, but they could vary with some schedule. And then the question is, do the same derivation where you derive what is the effective weight on each term in the average. So that's what's being computed in this exercise. The derivation is basically the same as this. You just have to keep track of the subscript on alpha through this. So that's what I've done here. In this sum, instead of this being 1 minus alpha, it's the n minus I. It's actually this product expression where we have the actual terms of the product with the subscript on alpha in
You
here.
start with a PDF and edit it. I mean, the thing on the left looks like it's typeset, which is certainly neater than my notes ever looked.
No. This has nothing to do with the PDF. I mean, I have typed these up to create notes for the book.
Including all of the typography. I'm impressed.
Oh, I mean, it's not that. I mean, this is just LaTeX. So I haven't included all the text from the book. I've only included text from the book that I think is useful to, explain it in the notes. I mean, there's also things in the notes that are not in the book if there's some, extra derivation. Right? This chapter in particular, towards the end, has a lot of extra notes on things that come up later in the chapter. So. Yeah, but there's if you go to this, it should also be linked in the meeting description, but there is static exports of all these notebooks you can just read whenever you want at this sorry, this is a local copy of it, but it's that there's a link to it from the GitHub repository that you can look at. So I mean, you can look at this too. This is I guess this isn't here. I should just go to the actual GitHub repo so that I can show you here. GitHub repo, this link on the right here, this is the link to the static exports. And then if you click this one, you can see, the exact notes I'm showing on the left here. This is like a non-interactive version. This right. These are all. It still has the code and all the information rendered in here, but these like plots, for example, are not anything. Like all these interactive things are disabled because this is a static version. This, what I'm showing here, is actually like running live. So all these things, all the interactive elements will work.
Clearly, I need to up my notes game.
Yeah, well, this not you don't. I'm not saying anyone has to produce notes like this. I really just made these so that to make the meetings better and to explain things more clearly. the earlier versions of these notes really just had the exercise solutions, and that was it. So yeah, I was saying that when we have alpha, which is not constant, then we have this slightly more complicated expression in here. It looks very similar to this, right? We just have these product expressions of alpha. But the nice thing, to verify that this is the correct answer, if we set alpha sub I to 1 over I, right, this is the non-constant value of the step size in the case of the sample average. Then we can plug that in this expression, this product. And if we expand out the product, we can see that all these numerators and denominators cancel here, except for the final term value of n in the denominator. And we just have this sum of r sub I over n, which is the sample average. So, this is the correct form for when alpha is non-constant. Typically, we won't. I mean, the only concrete example of non-constant step size we have is the sample average, which is this value of alpha. But there could be others. You could have alpha itself exponentially decay, or just stay constant as it is in the constant step size methods we have in the book. So then the next exercise is design and conduct an experiment to demonstrate the difficulty sample average methods have for non-stationary problems. Use a modified version of the 10-arm test bed where all the cues start at equal and take independent random walks okay, so this is like designing a non-stationary problem. Now it's saying to sort of copy figure 2.2, which is this. So this is the figure to show the performance of the epsilon greedy method on the 10-arm test bed, right? Where these are all stationary problems. So if we look down here, the non-stationary algorithm, right, is one where alpha where there's this initial value of the rewards of 0, and then there's this value of sigma, which controls how quickly the rewards drift up and down. So basically, over time, which arm is best could change, and the arm that is best, the amount by which it is best, will also change. But these rewards will drift over time, and then we are going to solve this problem. We can compare the sample average method and the constant step size method, right? So what this is showing is the performance in terms of reward over time, and this is average over a bunch of randomized runs. And right, the sample average method doesn't have any parameter that we can adjust, except for, of course, epsilon. So in this case, epsilon is 0.1 for all of these, but I can set it to 0.01 and run this again. I don't remember exactly how long this takes to run. Okay, not too long. So we can see that, over different values of epsilon, actually, it looks like 0.01 is a little closer to the theoretical limit here. This theoretical limit line is showing if I'm like cheating and I actually know which arm produces the best reward, and you sample from that every time. And then these other curves are showing the algorithms that are actually trying to estimate that value and keep track of it over time. We can see that as I change the value of epsilon, this value of alpha is somewhat arbitrarily selected at 0.1, but we can see that, it is outperforming the sample average method right here, both in terms of the reward collected, and also, this is over time converging to actually selecting the correct, like the best arm more frequently. And the sample average method is sort of stalled out around here, where it's not really improving, and it's selecting, it's successful less than half the time at identifying which arm is the best reward. So I guess, does anyone have any question about why the sample average method struggles so much in the case of this non-stationary problem? Or does anyone have any question about how the non-stationary problem is actually set up? It is described here in the text of exercise 2.5. But there is all the rewards start at 0 and then they all drift over time. So, there is this change in the average. It's like every arm is undergoing a random walk to adjust the value of the average. Yes, the epsilon. So yeah, this was covered in the previous meeting, but the epsilon greedy method is a method which uses this constant value of epsilon to decide how often to take random actions. And the random actions are used to make sure that we continue to collect data from all of the arms.
So given the drift, given the drift of the multi-arm bandit distribution, the sampling method wouldn't it be failing because actually never mind.
Yeah, well, if anyone else has, I mean, the point of this exercise is to show that when we have a non-stereo like this, so this theoretical limit is showing if we always selected the correct arm with the maximum average at that moment in time, this is the reward we would receive. If we compare it to figure 2.2, this is the same thing. Here, the theoretical limit is constant the whole problem because here we have these bandits, their reward values are not changing over time. So, and the difference in the non-stationary problem is that what is best is changing over time because the arms are drifting in their reward value. Of course, this random walk process, we still expect the average reward to be 0 because it's symmetrical going up or down. But because the variance is going up, right? As this process goes on, the average is 0, but the variance is growing. And because we have 10 different arms and we're ranking them, our expectation of the value of the best arm will actually grow over time. It will basically grow over time with the variance because we're ranking them. But, if we look at a plot of the expected reward of each arm over time, it would just be sort of expanding out on both the positive and negative side. But, we're only interested in tracking the actual, the maximum value of all the arms. But the main point of this is that the reason why the sample average method is not doing well is because it retains to all the information about the past. And in this case, the average values from the past are not relevant as we move on in time. We don't want to necessarily forget all of it immediately because we don't know how quickly the non-stationary problem is changing. But if we use a constant step size average, we do have a chance of tracking these values over time, like even if we're not doing it exactly right, because the past data, the information from it is decaying exponentially. It's decaying to 0 as we collect more and more data. So we're still able to smoothly track this. And we can see the sample average method, it is not improving over time because it's going to get, it's going to just take much longer. And I mean, even all the data it's collecting here, even if it does improve here, this data is going to become irrelevant, in the next, 10,000 time steps. And the longer we go in the process, the harder and harder it's going to be to learn new information. Actually, just as a little help here, this is kind of what I was describing before. This is showing with this random walk process, this is the expected mean reward for the arms ranked from 1 to 10 right? Where this blue line is the best one. So this is what we expect to happen to the non-stationary problem over time. And the goal is to be tracking, which arm is actually the best, right? This is just saying this is arm, rank 1, but we don't know which arm it is, right? It could be like the random process will actually determine which of the 10 arms is the one that ends up being rank 1. This dotted line is just the standard deviation of this drift process over time. And it grows like the square root of n, where n is the number of steps. That's just how the standard deviation grows of this type of random walk. So, okay. Question is, what is the model for our? So here, in this chapter, we're not dealing with the full reinforcement learning problem. Actually, the goal of this chapter is to take this problem where we have action. Now, in the RL problem, we will have actions. We will have to select the best action to take in a given situation. This 10-arm test bed is a test problem where the situation is always the same. Right? We're just trying to select the best action in the problem. There are not different states we have to consider. And the model in this case is just an estimate of the average of each arm, because this is a pretty simple problem. There are just 10 things we have to choose between. And we just have basically 10 numbers that are keeping track of what we believe to be the best action. In more complicated problems, you get sort of neural networks and other more complicated models in problems where we have, a lot of states, so many that we can't keep a separate estimate for each one. And then we need to have a model that lets us, generalize to the states where we have, an uncountable number, like an infinite number of states. And then, we would need some kind of model to extrapolate to states we haven't seen before. But in this problem, we can see all the actions, we can keep an average for each one of them. So the model here is very simple. And it's just, if you look at, in this problem, like this is the model, it's just the count and the average for each of the 10 actions. So just literally a list of k numbers, or 2k numbers if you count the number of samples. Yeah, I mean, this approach will also work for the full reinforcement learning problem, but it will only work in problems where these tabular problems where we have the ability to enumerate all of the states and actions that we care about. Okay, so any other questions about the non-stationary problem?
No, I did not have any other questions, since that conversation about the average, which doesn't have discounted rewards, and then having discounted rewards explains it decently of why the discounted problem eventually does better performance on a non-stationary problem than the averaged one.
Okay, great. So we can, I guess then in that case, we will move on to other techniques of balancing exploration and exploitation. So we had previously introduced the epsilon greedy method, where we have this parameter epsilon, which controls, how often we select random actions and keep track of the problem. Now there's this alternative to that, which is optimistic initial values. And in this case, instead of initializing our estimates at something like 0, now in this problem, 0 happens to be a neutral estimate, because the 10-arm test bed, the expected reward for an arm, for any random arm, is actually 0. We happen to know that. There could be other problems where 0 is not a neutral estimate. right? In this case, it happens to be. But there's this alternative where we can forget about the actual, epsilon greedy exploration, and we can just try to initialize our estimates with a value which is overly optimistic. And what that will do is when the algorithm is looking at the estimates, if there are some arms that haven't been sampled that much, they will by default be looked at as favorable options. And it's only after we've collected enough data from them that we bring the average down to a more realistic level that they will appear, to be worse actions. The goal of this optimistic initial values is the same as the epsilon greedy algorithm. It's to make sure that we, explore enough from the different arms. Just the mechanism of controlling why we explore different actions is different. And this is also different because the exploration will change over time with this. Like there will be the most exploration early on in the process because the average, is high. Whereas in the epsilon greedy method, there is some more exploration early on, but actually, the value of epsilon is constant throughout the whole algorithm. Here, what actually happens over time is complicated, and it depends on the order of rewards and how the averages change over time. So again, like to summarize, we're going to bias our initial estimates at a very large value. And then, that bias will ensure that we actually, at least collect some data. Like if our estimate is 5, now I think I have a plot earlier here of this 10-arm testbed and what the distribution is. Yeah, so this is a plot of like, if we have a 10-arm testbed, what do we expect the best arm reward to be? We can see that if we go out to 5, there's almost, a 0% chance. It's a vanishingly small chance of one of these arms actually producing an average reward of 5. So that's good, because then if we initialize our estimates at 5, it means that whatever arms have a few samples collected, those arms will continue to be sampled basically until we've collected enough data to bring their estimate down to earth, closer to a reasonable value. So what this plot is showing is if we actually run this algorithm, so with the Q estimate starting out at 5, what is the performance over time? In this case, it's only showing the percent of time the optimal action is selected. So here we're comparing it to the epsilon greedy method with epsilon as 0.1. And also with the constant step size averaging. I don't remember here if this epsilon of 0.1 is actually the best for this problem. We can just quickly compare it. 0.01. Okay, so 0.01 appears to be quite a bit worse. So we can also try like 0.2. Okay, 0.2 is like, so probably 0.1 is close to optimal here. So at least over this time scale, we can't, this optimistic initial estimate is beating the epsilon greedy method for this time scale. We could also tweak this to like 10 and see if that makes things any better or worse. It's actually about the same if we set this to 10 versus 5. Now this method will fail if we set this too low. Like if we make this only 2 instead. Oh, actually 2 is still pretty good. I guess because 2 is still a lot higher than the average best reward. Okay, I mean, even 1, I guess it's only, if we set this to 0, this will then mimic the epsilon greedy method with epsilon equal to 0, and that will be bad. So I guess I'm surprised that even a value of 1 works pretty well in this problem. But we'll set it back to 5. And both the learning rate or the value of alpha is actually the same for both of these methods. Now, there is this question about this. Well, first of all, are there any questions about how this method works? I guess there's no pseudocode for this. Do I have, I think if you look back at my implementation of the simple algorithm, Yeah, so I wrote this originally to have to be able to do the optimistic initial value method as well. Right, because this Q init, I basically would just to do this algorithm, I would just set this to 5, and I would set epsilon to 0. And then otherwise it's doing the epsilon greedy method with epsilon 0. So it never selects random actions due to epsilon. It only selects a variety of actions because of this. The argmax of Q will favor those the initially biased estimates where the initial bias is 5. Let's see. So any questions just about how this actually works to achieve the goal of collecting enough data from a variety of actions?
I guess, given, the nature of the problem, if you have overly optimistic estimates, it would, continue to sample things that are overly optimistic until it gets to the point where it's a realistic one.
Yeah, there's also a note here that this method will not work well in the non-stationary case, right? Because in the non-stationary case, we have to explore over time and track the changing problem. And right, this method like depends on our initial estimates, and that method of continuing to explore will not continue into the future. But we can look at this exercise 2.6, which is it's referring to this plot. And this plot, it looks pretty different from the epsilon greedy algorithm, which just has this sort of smooth improvement in performance over time. The question with this plot is, why are there these unusual spikes in this plot? So we have right around, and this is all like, these spikes are not the result of some particular run of the problem. This is using the same averaging method as all of the test bed problems where we have 2,000 different bandits, also thousands of different runs. We're averaging the performance across all of these random runs of the algorithm. And the question is, how come there is this spike? It happens to occur. We can actually zoom into the plot here as to see exactly what step it appears on. But it's not just one spike. There are other oscillations. Why are there oscillations in the early part of the curve? And the question is, why is the performance of this fluctuating so much in the early steps here? So in this plot here, I'll zoom in here so we can see that there's a spike on step 11, and then another little spike on step 21. And actually, if I make this, I'll make this a more extreme value, like 10. Now we can see actually more prominent spikes on step 11, 21, 31, 40, I guess 41. There, the spike doesn't actually appear. As I make this value larger, what you'll see is that the spikes will become more prominent, these oscillations. Here we go. 11, 21, 31, 41, 51. So there's clearly some kind of pattern here with the early performance of this sort of ringing oscillation. So I do have an answer, but first I'll wait to see. Does anyone would like to take a stab at why this is occurring in this particular pattern?
But it would be something with how it's essentially collapsing the early optimistic estimates with updates after each step, or something like that, where at one point it would choose one of those multi-arm bandits and then, collapse the original estimate and then go to another one. Or at least, but that doesn't really make actually, yeah, that kind of doesn't make sense if there's, number of actions being, 10 multi-armed bandits, I think.
Well, yeah, so these spikes are happening, on average across all the different bandits. Like it seems to happen regardless of which, whatever random one we have.
Okay,
The
so
amplitude converges. Honestly, no, I would say that yes, in some sense, there are oscillations going on all the time, and you can see that more, right? If I increase this value, you can see the oscillations continue longer. They do definitely go to zero over time, right? I mean, quite rapidly after a certain number of steps. So yes, there are oscillations, but the question is still, why are there oscillations in the first place? Not, as a bonus, you could also explain, why the oscillations disappear over time.
It's kind of because of the amount of overestimation of the expected value or something like that, I think.
Sure.
So
Well,
like
yeah, the whole premise of this method is that we start out where we set all of the initial estimates at a value which is much larger than the true value. And then, yeah, we're collecting data, actual samples.
Right, since everything's overestimated and everything's getting sampled, all the values start decreasing. Eventually, we kind of reach the expected amount of overestimation, like above what the actual top value is, and then we start sampling from that. And statistically, that kind of happens at around the same point. And then I presume that because values are changing, then we get a drop.
I'm sorry, which values are changing?
Are the values changing in this setup?
This is the stationary problem.
It's a stationary one. Okay, then I'm just confused.
Okay, sorry. There is a specific, okay, so keep in mind, like this first spike happens on step 11. Right, and then 21. Now this is the 10-armed bandit test problem. Okay. Now I'll just go into I have this explanation written up here, so we can just read through it. But keep in mind, so the initial values are high, they're 5. Now, the actual sample we collect is going to be much lower than that. In fact, let's just say, it's practically 0, right? So you can think of almost the average after one sample collected would be like 2.5. So what's happening early in the process is we are going to sample each of the 10 arms one time, right? Because whichever arm we've already sampled, its average will drop. It will drop below the other, the unsampled arms. Okay, so for the first 10 steps, we just collect a reward from a new arm. And on average, right, that's not the correct arm. I mean, there's a 1 in 10 chance. If you look in this blue line, right, this is the percent of time we are selecting the best arm. And you can see that it's 0.1, right? It's 1/10 of the time, because early on we have a random shot at picking the best arm. Okay. Then we have collected a single sample from every arm, right? Now, even though we don't know for sure, the sample from the best arm, the actual best arm, we would expect that sample to be higher than any other one. It won't necessarily be, but on average it will be. And this value at the spike, which is 42.5%, that is because we have a 42.5% chance on average that the sample we collected from the best arm is actually the highest sample out of all of the 10 ones. And as long as that's the case, then on step 11, we will then have a much higher chance of selecting the optimal action. Then once we've picked it, the problem is we now have collected a second sample from the best arm, right? All of the other arms, the other 9 arms, have 1 sample. The 10th arm now has 2 samples. And because we set our initial estimate so high, those 2 samples are going to tank the average of the best arm in comparison to the other 9. So then our chance of selecting the best action, on the 12th time is going to plummet because, we've now collected 2. Now, there is still, it's still better than the 10%, but it's, it's cut in half because the chance of collecting, 2 samples from the arm and having that average be better than, the 1 sample plus the initial estimate of 5, the optimistic initial estimate in the first arm, is very low. Okay, so if you see what I've written out here, we have this value of 5. We expect the expected Q value from the best arm is like about 1.539. And, if we look at this percentage is basically, we could try to calculate what the probability is, but it's the probability that for one of these random bandit problems, the sample we collect from the best arm exceeds the sample value from all the other arms. It's not 100%. It's about this 42%. That's what I've written here. On the 11th step, the Q value for each action is, and of course, this is all using the constant step size alpha, right? So as we update the average here, we have 0.9 times 5 plus 0.1 times the action reward. And the optimal action will be selected on that step as long as the reward produced by the best action exceeds all the others. Empirically, it's about 40-something%. And this is, this percentage would be higher if the arms had a larger variance between them. That basically the difference in reward from the best action to the second best action. The likelihood is that, out of, this 50-something% of the time we don't select the best action, it's probably because we are selecting, the second or third best action, because it's not that unlikely that the sample from that action would exceed the sample from the best action. So this is what, the updated average would be then. Like, let's say that for that 10th step, for the 11th step, where we then are selecting what we believe what actually is the best action. We're now going to have 2 samples, right, at this average. And those 2 samples will then change the estimate for that reward value to like 4.34. All right, here I'm just using the averages. This is what happens on average. Now, the second best arm has an expected Q value of about 1. Right, this is just from how the problems are set up. On average, the best arm is going to be 1.54. The second best is about 1. And with just a single sample collected from that, we expect it, now when we average the 5 with the 1, it's about 4.6, right? So the problem is now, like the 2 samples, right, for the best arm, this value is now lower than this value. So that's why on, the 12th step, this value is going to drop, because we would expect on average to lower the reward of this arm too much. Now, this whole process is going to continue every 10 samples in this case, because we have a version of this on step 21, right? It just involves more samples being collected. But we're always going to have a bias, like for a large part of the process early on, the values for arms that have been sampled less frequently are going to be higher, right? Just because of that initial bias. Someone asked, are there earlier recordings to watch? There should also be a third recording, which is the introduction to chapter 2, because we already did one meeting covering chapter 2. Yeah, so sorry, I have this here. I'm going to keep this right up on the screen here for a little bit. But does that explain to people why you have this spike every on the cycle of every 10 samples? It might be a little hard to visualize if you haven't. You kind of have to go in order and just imagine how the samples are being collected, how it affects the average values.
So at each step, you're taking a sample, but what are you doing to get that percentage of runs taking optimal action?
Oh, well, this is I'm here averaging the results over a bunch of runs. But see, because I know because I can see how the bandit, in the code, the bandit is defined. So I actually know which action is optimal. The algorithm doesn't, or the algorithm's trying to estimate that. But as part of this test bed, we actually know which action is optimal. We basically, right, this plot is showing when we create let's say 2,000 random bandits, which is just going to produce one of these things. So we have a bunch of these, inside of the algorithm, and this is the definition of the bandit. So it has a mean and variance for each arm, and we actually know these values. The goal is to evaluate how well the algorithm is figuring out, which one of these has the highest value. But it's the same thing here. Like in this figure, I know the theoretical limit here because I can look at the bandit, see which arm is best, and run the same process where you actually always select the optimal action. Oh, is there any other question about that? So the next exercise is a little, actually deriving it is a little involved. It's probably not worth going through all the details. If you want to read the notes and, look at it, feel free. But the point of this is if you look back at this equation, right, this is what average is being computed by the constant step size parameter. And you can see that we have this exponential recency weighted sum of rewards. We also have this term, which is a term of Q1, right? Q1 is either, Q0 is the initial value of Q, right? Q1 is actually our first, average after collecting a sample. And maybe Q1 is the initial. Oh yeah, sorry. Yeah, no, Q1 is the initial estimate. So, whether, you could say, well, just set it to 0. It still is going to bias our rewards towards 0 if we do that. There is no, neutral estimate here. The only neutral initial estimate would actually be the correct value of the average, which we don't know ahead of time by definition. So this method is going to have this bias to Q1. Now, luckily, this bias, right, because alpha is between 0 and 1, this bias decays to 0 over time. But we still have the bias early on. Now, in the case of the optimistic initial estimate method, we actually want that bias. That's how the algorithm works. But that's only for that method. There's plenty of other methods where we don't want an initial bias. And, the sample average method, for example, doesn't have an initial bias because, we just set the value to the first reward sample. That's the first sample average. And we can't do that for this method. However, there is a way to remove the bias from the constant step size method. And the way of doing that is to keep track of another value, which we do have to initialize at 0. And we have this step size beta that is a function of the constant step size alpha, but we divide it by this other value that we're keeping track of, this O sub n. And O sub n is updated this way. And if you go through the derivation, which I have written out here, and it's kind of tedious, you can show that what is being computed is this, which does have this dependence on Q. However, beta 1 is 1, which you'll see if you do this derivation. You can also see it here, beta 1. Yeah, if you actually compute this with O0 is 0 and then do this initial update, the first value of beta is 1. And therefore, in this product term, that is 0. So this product is always 0, meaning that our Q average that we're computing is no longer dependent at all on the initial estimate, right? So this is a way of removing that bias. It's just sort of something that's good to know. Whether you want to actually use it in a problem depends on what method you're using. You would never use it for this method because it will ruin your whole optimistic initial estimate setup. But this is a result that's relevant to things way outside of reinforcement learning. If you ever want to compute an average, sort of a moving average of a non-stationary problem, and you want to remove the bias on the initial, on your initial estimate. But yeah, I'll leave it. Again, the static exports of the notes is there for anyone that wants to read this derivation. So we can move on to the next method of balancing exploration and exploitation, which is upper confidence bound action selection. So far in all the methods, we have been selecting the action on every step using the argmax function, but we've taken the argmax of the Q values, where Q is the list of our current estimates for the different actions. In upper confidence bound action selection, we still take the argmax, but we don't do it on the Q values. We instead add to every Q value a quantity, and the quantity involves the square root of 1 over the number of samples that have been collected. There happens to be also this natural log of t term, where t is the number of total time steps that we've run the problem for. This looks a bit like some kind of black magic, and that's because this is a heuristic which has been experimented with over time. The origin of this, however, is kind of clear. The goal here is to add to our estimates something like the variance or the standard deviation of the estimate. So the point is, like, if we already knew what these Q values were, then the problem would be solved. We're assuming that the estimates we have are not entirely correct. So what we think of as the highest value might not actually be the highest value. Now, one way to deal with that is to say, well, if the samples we've collected is very limited for a particular action A, maybe we should just take a really optimistic version of that estimate where you say, this is a high variance estimate. Let's just add, some value to it, which is related to our uncertainty in the estimate. So that way, if we have a high uncertainty of certain actions, then we're more likely to sample them, even if the Q value itself is not that high. And this is a way of controlling the exploration on not just on average, like with the epsilon greedy method, we just explore random actions and some fixed rate. This controls it at a more granular level, where we're controlling it, for each individual action, we'll have a different quantity, which controls our likelihood to explore it. But, the formula is presented here without any kind of formal derivation of it. And that's because there isn't really, a clean derivation of this. It is inspired by the variance of the sample average. But, that's just an inspiration. Like, that doesn't explain why there's this natural log of t term in the numerator. This just makes sure that even as the number of samples gets really large, there is still a growing chance of exploring as we go out to, an infinite number of time steps. But yeah, here, stated here also, the square root term is a measure of the uncertainty or variance in the estimate of the value. Isn't it from Wolfgang's inequality? Perhaps. I'm not sure. I don't know off the top of my head what that expression is, but I mean, the origin of this whole, square root of 1 over n is from the variance of the sample average. Is that this is how the variance of the sample average is proportional to this. So I hope, for anyone studying probability theory, it's a common result. If you're studying the distribution of the sample average, this term will often come up. So, this kind of like the epsilon in epsilon greedy, in the epsilon greedy method, this also has a constant c. C is just a constant. It is a free parameter of this method. There is no way to know what it should be. It is something that has to be experimented with, just like epsilon. There's no way to know ahead of time what the optimal value of epsilon is. And so come up towards the end of the chapter, there are these parameter studies of these methods where we see how do the methods perform with different values of the free parameters. But yeah, any method that has any free parameters, even one, it is something to take note of, is that you have to have some way of testing different ones. Ideally, the method would be very robust to different choices of the free parameter. If it's really sensitive to this, then you don't have a very high chance of success, because you would have to, know ahead of time a good value of this, or you need enough resources to run the algorithm testing different values of C, which is what we end up doing in this chapter. But that's more to evaluate the algorithms, not that you would actually, want to do that in real life, because we don't have infinite resources usually when we're trying to solve a problem. But here we have the performance of this method compared to here. This is also showing the reward average, right? Not the actual correct action selection percentage, but the reward average. But we can see here that actually the UCB method with C equals 2 is actually quite, even after just 1,000 steps, is getting quite close to the theoretical limit of performance. We saw that over this number of time steps, a value of epsilon of 0.1 is pretty optimal. For this method, C of 2, I don't remember how optimal C of 2 is. Okay, I mean, C of 1 we could see is actually even better. It's even more quickly approaching the optimal. And if I set it to some high value, it's probably bad. Yeah, so that really tanks the performance. Probably the reason why C of 2 is selected in the book is so this spike is more prominent, because there's an exercise asking about this spike. You can see again that as I raise the value of C, we exaggerate the spikes, kind of like the optimistic initial value method. And actually, the spikes are occurring on the same exact time steps. So it should be some clue as to the origin of these spikes. It is related to the origin of the other spikes. You could see that, as I make C larger, kind of like increasing the value of the initial estimate, this is also exaggerating the spikes for a longer period of time. They're also occurring, right, every 10 action selections. But I guess, well, first of all, are there any questions about the UCB method to begin with? Because then we will move on to answering this question about the spikes. If not, also think about the spikes in the same way as they appeared in the optimistic initial value method. Yeah, this is the selection rule for upper confidence bound. Yeah, your question is, why is it said that when NA is 0, that is a maximizing action? Is that only in my notes, or do you also see it in the book? I know I have written it here. It's in the book. I'm sorry, where in the book is it?
It's the second line on page 36. If and the second line, the one above that.
Oh, here. Yeah, exactly. So if this is saying if we have no samples from an action, the variance is infinite. We have no information about it. So basically, any action that has never been sampled is considered to be maximizing. Meaning we should assume it could be the best action. Often, right, when we start the process, all 10 actions have 0 samples. So then every action is considered maximizing. So we would randomly pick between them. As we collect more actions, then there might only be one left, which is unsampled. But basically, any action which is unsampled will always be selected prior to another action in this method. Yeah, however, in this case, instead of being related to the optimistic initial value, we have initialized all the values to 0 in this case. But this expression, it's not optimistic. It is it's actually more right. This is expressing paranoia about not having an accurate estimate. So it's saying if we have an action which has 0 samples is the worst case, 1 sample is pretty low, we are going to add a lot to it to assume that we have dramatically underestimated its average, right? That is one way of guaranteeing that we explore actions thoroughly. So, if you take this process a long time and there's one arm which appears to be really bad and we have a lot of samples from the other arms, eventually, if that arm only has 1 sample, eventually this term will grow so large that we will select it over any other arm just as a way of being more sure of what its average is, right? Because as we reduce the uncertainty, meaning we collect more samples, we will shrink this term. So this selection rule is a way of balancing what we know to be the good values with minimizing the uncertainty of those values. But yeah, we've kind of, this note actually answers this question, which is, why does the spike happen on the 11th step? The answer is sort of the same reason as the other method, which is that, right, for the first 10 steps, because of this term, because of n being 0 for all of those, we are going to select all of the actions once. Then on the 11th step, n is the same for all of them. So this term is equalized across all the actions. And then we're left with this term, which we would expect that what actually is the best arm to have produced the highest average reward, which is why there's this large spike in the success rate on step 11. Because, right, step 11 is when we've equalized these. And the same thing happens on step 21, right? On step 21, again, if we sample all the actions again once, which we're likely to do if C is large, right? Like the larger C is, the more weight is on this term. And then we're going to add a second sample to all of them, and then a third sample, right? If C goes to infinity, this process will continue where we will just evenly sample across all the arms until we have shrunk, this term enough that we start caring more about the average value, right? I have a more detailed explanation here of exactly, what the values are expected to be. But yeah, the initial spike for sure is very closely related to this statement, right? So this is the reason why we will always select all 10 actions from the start, right? Like we will never neglect an action in the first 10 selections, because until we've selected all 10, one of the actions will have n equals 0. So that will always be considered maximizing. I hope. Any other question about this? Yeah, there's just no, yeah. If C is 1, the spike is less prominent. Yes, so the spike magnitude, changes the value of C. It's still there though. It's just not. It's very small. Just right there. Okay. Well, if not, we can move on to the gradient bandit algorithm. These are actually, this is a substantially different way of controlling exploration. So far, all the methods we've looked at are trying to directly estimate the average value for each arm. The gradient bandit, if you just look at it here, it's why in my notes I have a more detailed explanation of where this whole expression comes from, which sort of gives it some context. This is sort of presented out of context in the book, where we just create a function h, which is supposed to be like the preference of an action. It has no meaning other than how we update it. We also have a probability distribution across which action we're selecting. So here, unlike in these methods, we're just using the average, which we're collecting, and then we have this method of action selection. In the gradient bandit method, we have a completely different method of action selection, which is probabilistic, where we actually have a probability distribution across the actions, which is computed from the preference function using a softmax transformation. For those who haven't seen it before, if you have any scalar function of multiple, output values, you can transform that into a probability distribution with a softmax function, which just means that, it meets the properties of a probability distribution, where all of the values are, between 0 and 1, and the sum of all of the values is 1. That is the purpose of applying this transformation. Now, in order, there's this derivation here on how to actually derive the update rule here. It's actually a form of gradient descent when we collect samples. It is, as you can see, actually, yeah, the derivation's pretty long. We probably should just save it for the next session, because this whole section, I mean, what we've been talking about so far in this is sort of sample averages, how we collect them, and how we use them. The gradient bandit is a totally different method. Do they actually have pseudocode here? Yeah, this is the update rule, which, without actually going through this derivation, is a little hard to explain. But when we collect samples now, we can see it does depend on the reward. However, we're actually computing a gradient and we're updating h rather than q. And I have some more detailed discussion here of how the gradient bandit works, which we can go over next time. And then there's a section on, okay, associative bandits. Yeah. So we are basically at the end of the chapter, but, tabling the gradient bandit discussion for now, this summary has the parameter study in this chapter, which is a really good way of studying how the techniques work and what their advantages are. So previously we had these charts like this, where we could see how the epsilon greedy method works over time. What this is showing is if we define 1,000 time steps, and we're interested in which algorithm performs best over 1,000 time steps across different parameters. So in the case of the epsilon greedy method, we have the value of epsilon, right? In the case of the UCB method, we have the constant C. The gradient bandit is a little different. The optimistic initial value estimate, the quantity is the actual initial value estimate that we're using. So this x-axis is whatever parameter is relevant in question for that algorithm. And then this is showing the average reward over the first 1,000 time steps, also averaged across 2,000 of these different random bandits. And this is also a way of seeing how stable the algorithm is across different hyperparameter selections. This value, like the value of C for this, for UCB, is like considered a hyperparameter, just like, in any other deep learning context, you have like the learning rate, things like that are considered hyperparameters. So this whole chapter culminates in this parameter study, which I also have here. In this, I have it. I also have this other method here, which I can go over next time, which is a different idea of doing the exploration, exploitation balance. Also on my plot, these dotted lines are actually showing not just the average performance, but the variance of the performance of these algorithms. So you can see where the dotted line is, what the spread of performance is across the different algorithms. But you can see the broad results do match with the UCB algorithm performing the best. We can actually zoom in a little here. So we can see this light gray line is the UCB method. And these blue dots are the ideal performance, like the best you could get if you were to cheat and select the best action every time. So there is also this bonus exercise here, which is to do the parameter study for the non-stationary problem. Here they actually have, this is only for 1,000 time steps for the non-stationary problem, because it takes a lot of steps for the non-stationary problem to actually become interesting. This is over more time steps, and we only care about the performance on the last 100,000 steps. But we can see here, this is the parameter study for the non-stationary problem. You can see the parameter range has to be a little bit larger, and there's a few more methods here. I've also included in here the SAMP. So we have, if we just look at the UCB method, this is kind of illustrative. So because this is the non-stationary problem, we would typically only consider the constant step size averaging for this problem. And here, like, you can do any of these methods though with the sample average, even though for the non-stationary problem, that shouldn't be what you use. We can see here the gray, or the UCB method actually kind of, it works almost equally well for both. The difference, however, is that for the sample average one, which is here, you can see this curve is a lot steeper. So it's a lot more sensitive to the value of C. This value of C happens to work well. Whereas for the method we should be using, the constant step size, it performs better across a wider range of hyperparameters. We can look at a similar kind of thing for the epsilon greedy method, right? So here's epsilon greedy with the sample average, right, performing much worse than epsilon greedy with the constant step average. And I've included the similar comparisons for the gradient bandit as well, which, yeah, in this case, it's actually quite similar between the two. This makes more sense because in the gradient bandit, the averages are not used directly to select the action. They are just used as a way of reducing the variance of the gradient estimate in the algorithm. But for all the cases, right, you can see the biggest difference in the epsilon greedy case, where the sample average, has a lot of problems for tracking the non-stationary problem. So yeah, for next time, there will be some, if people are interested, I mean, we could either move on to chapter 3, or we can go over some of the more details about the gradient bandit and also exercise 2.10. And then most of these additional notes are actually more ways of explaining why the gradient bandit is written the way it is. But the gradient bandit ends up becoming somewhat relevant when you think about actually the very end of the book that we had covered a few weeks ago. But the policy gradient methods are also methods that use, like, directly compute a probability distribution over actions and use that to select actions instead of some indirect method with estimating the value of actions. Yeah, I also have these other notes also explain what this curve is, which is this is actually a sort of parameter free method of doing the bandit problem, which is inspired by the UCB method. Yeah, but makes a little, it's not exactly the same as this. It instead tries to more directly compute what the variance is and do something based on that. So yeah, see, chapter 3 of the book introduces more of the formal math behind reinforcement learning in general. So yeah, we'll decide, I guess, how much of the remaining details of chapter 2 we want to go over, and then we'll see how much of chapter 3 we get into. But are there any other questions about what we've done so far today, or any preference about what we focus on next time? Right. So if people want to contact me or ask questions, you can certainly write in the meetup discussion section. You can also write this GitHub repository is where all the notes are, and you could certainly create, well, yeah, it depends. Oh, there is a discussion section here. So you could also open a discussion here. And I believe my email is included in somewhere. If not, I can, here, if people do want to contact me, I will, I'll just write my email in the chat. That's one way, but it depends on, I guess, how, oh yeah. And the Discord. So actually, if you just have like a general chat question, the Discord is a good option. If it's something related to the notes and what, how an explanation is written, or how, the code is working, or if you're unable to run it on your own computer, then I would do it on GitHub somewhere. And then, if you have a more private question, you can either email me or send a private, a direct message on Discord would also work. But if people, Evelyn, is that link you shared the actual invite link to the Discord?
That's an invite link, yes.
Oh, okay. Yeah. So if anyone's not in the Discord and wants to join that link, it will expire. So, you should use it now. Are POM DPs and MDPs related to RL? Yes. So actually, the discussion of reinforcement learning in this book is formalized around MDPs, Markov. So yeah, Markov decision processes form the entire mathematical basis for the study of reinforcement learning in this book. The subject of POM-DPs is not directly covered in the book, although actually all the techniques in part 2 of the book, which deal with approximation, those also, they are related to POM-DPs, in that like you can always take an MDP and then make a version of it where some of the information is not available in the state, and it's just effectively a new MDP. Or in the case of approximation, we by definition don't have access to the exact state. The approximation function only has access to a representation of that state, and that ends up being the same type of problem as where we have partially observable information about the state. So it depends on how, but yeah, the really part 2 of the book is more appropriate to the case of POM-DPs, if you mean the aspect of POM-DPs where you're missing information about the state, because that's exactly the situation you have when you use approximation techniques or the value function. And yeah, the actual discussion of MDPs begins in chapter 3. So any other questions or comments about next time? Again, I'm not sure if next time we should spend any time on the remaining parts of chapter 2. It is like more of a bonus discussion. Well, I did do it the last time we went through chapter 2, and that's where I sort of added this information to the notes, but it's not it's not immediately relevant to what comes up in chapter 3. To catch up, I mean, if you watch the past 3 lectures, that would pretty much completely catch you up, because I don't think there's any other information unnecessary so far that wasn't covered already in those 3. You could read the notes, like if you look at if you go to the static exports of notes and you look at chapter 1 and 2, and you can look at it with the book. A lot of it is repeating what's in the book, but then there's also the exercise solutions. I don't know, you may want to actually try out the exercises and then compare it to these answers. That, sure, actually doing the exercises is also a really good way to catch up and check what you know. Okay, well, if there's no other questions, I guess I will thank everyone for coming, and hopefully see you all next time.